Thank you for this opportunity. I certainly appreciate it and appreciate the opportunity to explain and kind of show one way in which we have taken an NSF grant and with that then use that to combine it with a peer grant and to be able to leverage that opportunity. And so the broader work here was funded by NSF, about a 3-year project, $750,000 to do a suite of discrete element modeling, numerical modeling, or continuum modeling, lab testing, and centrifuge testing. But as we were going through that project, we realized that there were certain gaps in our data that we would benefit from significantly if we were able to fill that in some way. And so that was at that point that we went to peer and we said, hey, we have this larger project that's going on, but if we were able to complete a couple more experiments to fill in some of these knowledge gaps, it would make a much more comprehensive story and be able to understand things. And so in the context of that, I just want to walk through the project as a whole and then provide some highlights, particularly in the areas where the work funded by peer, which financially was only 10%, but maybe in terms of knowledge generation was a much larger percentage of that came from this project. So the work was done at UC Davis using the centrifuge facility in collaboration with a couple other colleagues, Katerina, who you heard from this morning regarding the facility, as well as Alejandro Martinez, Dan Wilson, and several other postdocs, visiting scholars, and graduate students. So let's just set the problem first of all. We know that performance-based evaluation infrastructure comprised of or founded on gravelly soils is a highly uncertain endeavor. It's not easy to predict whether it triggers or not, but it's even much more difficult to predict how it's going to behave, and in particular what the strains and deformations are going to be throughout that structure. We know it can trigger. There's several case histories that have documented that, and in fact there is evidence that more gravelly or well-graded soils, because of its higher stiffness and lower void ratio, could actually generate pore pressures and trigger perhaps even sooner in an earthquake event than regular poorly graded sands by a cycle or two. Or perhaps more. However, the challenge comes really again in prediction of the subsequent strains and deformations that are realized, and that's because we have done for this problem, as we do for many problems in engineering, is we've moved and kind of drifted from our knowledge base or our home base, which is in poorly graded sands at shallow depths, and we have from there said, okay, well we also have to solve this problem for gravelly soils. Let's take these tools and let's just transport them and see how that works out. And it's not perfect. We can take a step back and I can say, okay, let's consider a hypothetical kind of cross section. This actually comes as a mock-up of the Pleasant Valley Dam near Bishop. And so you have this silty core type of material in a darker brown. You have a natural alluvium material shown in yellow, and you have a pretty well-graded downstream and upstream shell. In all cases, all those gradations don't match our database or our knowledge base, and they're all extensions as you move across the spectrum of larger particles and broader gradations. And so at a very fundamental mechanics kind of element level, I thought this is the chance to put in some void ratio and critical state terms into the conference. We can just say simply that the particles can pack much tighter together. Our void ratio can drop in half. Hydraulic conductivity can change substantially as well, but these map to significant changes at the element level with respect to state, stress dilatancy, and the critical state lines themselves. All those in aggregate affect all the tools we use to then evaluate the liquefaction procedures and the subsequent deformations. It affects the penetration resistance, whether we're using the CPT, DMT, IBPT, anything else, it's going to affect those because those have first order dependence on stiffness and on peak strength typically. It's going to affect how the pore pressures are able to generate, which is going to map to the triggering aspect. And then really ultimately from a performance-based perspective is what's happening with respect to shear strain accumulation and permanent deformations. And so current practice follows this basic flow chart. And there are tools and methodologies for each of these. And so it requires that we begin with the characterization step at our facility, both of the native, typically alluvial material underneath, as well as the embankment materials up above. And so we have a penetration measurement with some tool of some kind. We know we have to make a series of corrections to that, and perhaps we have to make more corrections because of the gravel content or the particle size. And we have to estimate the in situ state of that material or relative density. Now we just have a proper handle on our site conditions, hopefully. And now we have two questions, usually addressed in sequence, which is, will it trigger? Under what conditions will it trigger? And then if it does, then what will be the subsequent strains and deformations post-triggering? Are these materials susceptible? yes, in many, many cases, gravels are fully susceptible to liquefaction triggering, provided you don't have plasticity, and the permeabilities are roughly the same as sands. So that's our conditions. The reality is that we have come to learn the hard way that every step of this really needs to be revisited and either revised or expanded to not just consider poorly graded sands, but to be able to accommodate the spectrum of changes in particle size and in gradation as well. And so for us, this was our fancy, convincing argument in the NSF proposal of all the things that we are going to do. I know you can't read that, but in essence, it said we'll go back through the case histories and we'll do the suite of tools. We'll do some lab work, we'll do some numerical simulations, in situ testing, and centrifuge modeling. And I want to kind of pull back and show a little bit about how the importance of the peer opportunity played into this. And so we went back and compiled documents from a series of projects, some of which were liquefied gravels. Other ones are just the well-graded soils used in a lot of dams and embankments in different places. And we identified the following trends. And this is the simplest parameter we have, which on the left is your Emax, or your loosest packing. And on the right is your Emin, or your densest packing. And you can see that there's a critical zone at a coefficient uniformity, or breadth of gradation, from about 2 to 12. And when we laid out our testing program originally, we built a series of different soils. And for the test I'll show you today, we've tested 2 soils in the centrifuge to evaluate embankment performance. And those are captured in these gray lines that you're taking a look at here. We knew we wanted to anchor it in poorly graded soils, which is at the low CU value of about 1.7. And we thought we want to get to something which is reasonably well graded, and that falls in at about a CU of 8. But we're still not covering CU of 10, 20, 30 all the way out. And thankfully it plateaus, but we did not get out to where that plateau was. And this was the opportunity as we came to here and we said, hey, we want to add 2 gradations to kind of fill out this matrix, and most importantly, push to the right-hand side where the soil is well graded, and we're getting at a pretty, to the kind of the limiting asymptotic condition of a minimum CU value. I want you to note or catch here that as you go from the left to the right-hand side of these figures, the void ratio is dropping in half both times, which is a substantial change if you start considering particle scale aspects of rearrangement, interlocking, dilation, etc. I think maybe I should talk louder to compete with the loud voice next door, huh? So you can see those 4 different soils here. You can see visually what those look like on the top left. And again, importantly, these were the 2 base soils that we tested in loose and dense conditions with the NSF. Personnel resources we had, and the peer provided additional personnel resources to fill in those additional conditions. And that became pretty critical. So let's move now into why we have a position and really a belief that we have to go back through all of the entire process and reformulate, recast it. And so the first thing you're looking at here is simple monotonic experimental tests. We've also just submitted a paper on the discrete element modeling component of this as well. And you can see on the left-hand side, for those of you familiar, the critical state line, the poorly graded soils are at the top, and you can see it drops all the way down as you go to the more well-graded soils with the slope becoming flatter. And the flattening of that slope actually is what lends itself to a more rapid generation of pore pressure conditions if you have an initially contractive state. In the middle plot, you can see that peak strength going up as you become more well-graded, but also notice that the critical state friction value at the end, or at higher strains, is basically constant. So we don't see that changing, and that's a very consistent observation in literature. And you can set this into a Bolton stress dilatancy kind of framework on the right-hand side, and we can map this through for generalization to other sites and other materials. This work was led by Alejandro Martinez for the monotonic traxial work. Katarina led and directed the cyclic laboratory testing on the same complement of soils. Looking at 2 results here to exemplify that. The left-hand side being a poorly graded, right-hand side being a more well-graded soil. And these results, as well as results by Ada and others, show that the initial triggering generation of an RU of 1 pore pressure can occur at the same number of cycles or even less. But you can visually see that you don't accumulate strains once you trigger at nearly the same rate. And that's one of the most important parts. And we have some DEM wrapping up on that as well. We're going to skip a few steps, but in the program, we went from those lab tests to penetration resistance and some state parameter analysis, and then we went to the centrifuge and the performance. So we're just going to jump straight to the centrifuge and the performance part. So this is the 9-meter centrifuge facility, the larger one at Davis. You can see the model on the upper right-hand side there. We're at 40 times gravity, so that's a container that's roughly 1.9 meters in length and about 0.3 meters in height. And at 40 G, we're representing a slope, which is almost 10 meters in height, or 7 or 8 meters in height, over a run-out distance, or a horizontal distance of about 30 meters. We designed the shaking motion in this case to have, this comes from the LEAP program and we modified it slightly, but we have a linear ramp initially, where we're interested to see, as that amplitude increases, how fast do the pore pressures track with that shaking intensity. And then we want to hold. And we want to hold so that middle portion is a little bit more like laboratory tests at a constant CSR. And we're in that phase, we're able to track and observe kind of the strain accumulation that you're getting. If you have generated an RU of 1 when you get to the beginning of that hold cycle, then from there on you can see how are your strains ratcheting up for a few cycles. And then the last part we have is an exponential decay function, which doubles the length of the overall motion. And we have that because if we have stronger stress dilatancy and in the model and it's stiffer, then that means we should get more rapid dissipation of pore pressures during amplitude decay, and we should see a resting of deformations earlier. And so that's what we're trying to suss out in that simple kind of wave event. We have 5 different ones of those. We're just going to show you one of those today. And then we have 2 sets of sensors. In the bottom right, you can see a bunch of the sensors running into the model, which is pore pressure transducers and accelerometers, to be able to track the pore pressure generation and the dynamic strain history during shaking. But we also are interested in the permanent or the low frequency accumulation of deformations and strains, and we're capturing that using a series of high-speed cameras sitting on each side of this model. And then we can couple the PIV results at the lower frequencies with the accelerometers at the higher frequencies and get a stitched together response. So for sake of time, we're just going to look at the response in the upper part of the flat slope on top, though it does have effects from the sloping condition, as well as in the mid-slope. And hopefully this triggers, what you're going to see is on the top is the more well-graded material. This is shake 3, a 0.16 G shake, roughly. And you can see here shortly, you can see the ratcheting down slope that occurs on the more poorly graded soils up above. And in the bottom is the same relative density material, and therefore in our current design practices, it's all anchored in relative density, so we'd be using the same relative density in that case. But you can see that the deformations are pretty indistinguishable. I think this will cycle again here in a second. Here we go. You can also notice in the top model, you can see that those strains next to that red line on the upper right, particularly, those are generated all the way through the slope to some pretty significant depths. Whereas in the bottom model, we only have deformations really pretty near the surface in that case. And so that's a pretty surprising and significant result. They both triggered literally within the same half cycle, but the performance of them is significantly different, and that's what we need to learn how we can get right or how we can improve on. So let's get into at least some of the responses. We're at the upslope condition on this left-hand side. Poorly graded material is above in the black lines. And you can see, first of all, in the accelerations, after a few initial spikes, we're in a liquefied state. We have high excess pore pressures. You can see that with the black lines. Can you see that or not? Do this. You can see that in the black lines here coming across. We have significant excess pore pressure in RU of 1, and during dissipation, you can see it rise due to the upward flow. And it takes 300 seconds or so for it to fully dissipate. The well-graded soil, you can see you have dilation spikes at each stress reversal during the hold phase, the maximum part, but see our pore pressures are still the same. And we still have upward flow, so we're still liquefying. We have upward flow of that material, but look how much faster the pore pressures dissipate in about 1/5 of the amount of time, roughly. If we move to mid-slope, we now have the static shear stress that's contributing to this. And now you see a strong positive, which is a downslope bias, that you can see in both elevations of the accelerometer, strong spikes in that case. And that corresponds to the strong negative spikes in the excess pore pressure. Notice also that immediately at the end of shaking, the pore pressure drops to a certain extent, and that's because of the static shear stress bias that locks into the slope. But you still have substantial time in dissipation, and these times for dissipation are basically comparable to get to about a T90 value. In contrast, if you look at the more well-graded slope, you have strong spikes, they're capped off in the figure plotting, strong negative spikes in the excess pore pressure, and you can see rapid drop in pore pressure and then very rapid drop here. So it ceased much earlier. During this shaking event, the dynamic cyclic strain, cyclic response, you can see here at the right, you have the initial, it's colored based off of the cycle number going from blue to red. And you can see early on in the blues, we generate some dilation. And as soon as we liquefy, we have just a flat line response, which is not surprising. And the strains run the order of about 2%. The poorly graded material, same thing in that we generate a pore pressure. We have a little bit more negative pore pressure, and that results in still seeing that we're mobilizing some dilation at each of the stress reversals. So there's certainly an inherent resistance as the soil becomes more well graded to allow larger strains to occur. The particle rearrangement that's required for that forces dilation to happen, which is causing an arresting response, if you will. Mid-slope, everything just becomes biased in the downslope direction. You can see the strains here, in this case, are about plus or minus 4% and drifting back and forth. Even for the well-graded material, you are generating some dilation, but it's ratcheting and it's moving to the right. Whereas in the more well-graded case, right below the surface, very tight, very constrained. This is a liquefied material, but it is, you could argue, a very stable and somewhat predictable material if we can adjust our analysis methods to that. One real question, if you're thinking about deformations or performance, is how much time does the soil exist at a high excess pore pressure such that it would be more susceptible to deformations and to straining? And a very simple metric for this is to look at the first time the pore pressure exceeds 50% of the overburden stress, and then how much time before it actually drops down during dissipation. So as you go from the well-graded in, the poorly graded in gray to the well-graded in dark blue, you can see that we drop by about 80% in terms of the amount of time that the system will stay at a low effective stress. This was surprising. This is something, honestly, we didn't anticipate either. And we were scratching our heads why, and part of that was because we designed the test so that the hydraulic conductivities, the permeabilities between these two are exactly the same.